Good afternoon, everyone. So I was asked to give you an introduction to general relativity with a mathematical flavor. So if you already have said that course's introduction to general relativity with mathematical flavor, please leave. I mean, it's going to be a complete waste of time for you. This is course is directed to people who haven't heard much about general relativity, but know differential geometry. So I'm going to assume that. And the idea is to do 3 parts. So part 1 would be a little of causality theory. Let me actually start here. 1 would be causality theory, and that's for today. The second part would be about black holes. And the third part will be about the Cauchy problem. And so I have, I'm planning to do this in 4 lectures. The last lecture of the course would most likely be again a lecture by Professor Aichelburg, coming back to the physics of the problem. And this is going to be an introduction to these topics. What is this story with causality theory? Well, let's start with this, chapter 1. Causality is a bit of a boring subject, but it has it's used all over the place. So essentially, the aim here is to define global hyperbolicity. And this requires futures and pasts. And these are notions which show up both in the Cauchy problem, shows up in black holes. The causality theory as a closed theory had a big success with the singularity theorems, which are not really singularity theorems, but maybe Lorentzian incompleteness theorems, so telling you in some situations the space-time cannot be geodesically complete. And part of the Nobel Prize to Penrose was probably for developing this theory and culminating in his incompleteness theorem. So this is, but somehow it's a topic which is needed as a language to these things, but it's dead in the smooth form. It's everything what needed to be said about this was said 50 years ago, except that now there is a revival of these problems with metrics of very low differentiability, and I understand that you are actually concerned with things like that. But I will not talk about low differentiability causality because it's a topic which would just take me the lectures, all the lectures by itself, so that will miss the point of an introduction here. So good, so causality. Well, let's start with the setting, right? So what is a Lorentzian manifold? So that would be a manifold, and I'm assuming all manifolds to be well behaved, so are compact, Hausdorff, smooth, and what you need with a symmetric, degenerate, symmetric, well, actually not degenerate, tensor field, so two covariant tensor field. And with a specific signature, so signature, whatever this means for a tensor field, so let me just comment on this. The signature should be minus plus 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 in my convention. And signature, if you're a mathematician, probably want to do the following. Well, you have this symmetric to covariant tensor field, so let's call it G. And with it comes an each tangent space. You have a quadratic form, which is G of XX, right? And the signature of this quadratic form should be minus plus plus plus. which is the same to say that at every p in your manifold, there exists a basis of the tangent space, so that G takes the basis would be EA. And by the way, I like to work in dimension n+1. So n space and 1 time, so dimension is n+1. So that G, if we just take the scalar products of these, well, we use this tensor to take scalar products, and it's called a Lorentzian metric, but of course it's not a metric because the metric would be positive definite. So this is my Lorentzian metric, then this should take the same value as the Minkowski metric. In other words, this is a diagonal metric, or diagonal tensor with -1 and 1 center diagonal. Okay, so that's what a Lorentzian manifold is. And what is a space-time? And before I go to space-time, I need to define a time orientation. Before I define a time orientation, let's look at the something which is called the the causal character of the vectors. So if we take a vector x in a tangent space, then we say that x is time-like. And maybe let me just take this vector to be non-zero, because I could never make up my mind concerning what x should be if it's 0. So x is time-like or null or causal or space-like. If, well, we just take its length, we call this a length, this, if you want this value of this quadratic form on it, if the, so if g of xx, and now it's going to be, well, time-like is negative in my signature, null would be 0. Now, of course, if it's negative, it cannot be 0, but if its length is 0, it could be 0, but keep in mind this, right, that I'm assuming it's not 0, right? So null vectors cannot be 0. Causal is smaller or equal 0, and same caveat, cannot be 0, and space-like is whatever remains. And if you have a good reason to tell me that 0 is space-like or causal, just tell me. Just have to explain this to me, but I don't have a good idea here. So let's, 0 is just not in this classification. Well, one reason why I don't want 0 for in the causal region is that we're going to talk about curves which are causal, and so it means the tangent is causal, and then you don't want the tangent to be 0 because then the curve will be staying at some place. Maybe you want to avoid this. So you don't want 0 to be a causal vector and a space-like. Well, why 0 should be a space-like? Maybe. Anyway, so good. So this is these are my vectors. Now remember that's a Lorentzian metric. So in this basis, which I have at every tangent point, the metric looks like, well, you have an orthonormal basis. So if you take a vector and you write it as 2 vectors and expand, or let me just take one in this basis, then it's just going to be minus x0 squared. So it's same as in Minkowski space-time. So it's easy to understand in this basis what causal vectors are, or time-like, null causal space-like vectors are. And of course, well, in the general basis, then this does not depend upon the basis, right? So it's going to look the same as what I'm going to draw here. And of course, the drawing is clear. Right, so if this is negative, for example, say negative, then this means that x naught should be larger than the space length of your vector. By the way, both in special and general relativity, one always writes time going upwards, which is opposite to what one does in mechanics. In mechanics, time always goes down, so don't get confused by that. Small velocity in mechanics would be that the graph is like that. Small velocity. Special relativity, general relativity will mean that you're actually on a curve which goes straight up. Good. So of course I'm removing 0 from here, right? So this point is missing, and then time-like vectors are those so that the length of x naught is larger than the length of the space part. This would be just this part which doesn't involve the 0 component. So time-like vectors will be inside this cone or inside this cone. So there are two components of the set of time-like vectors, and you have to make a decision which one is which. And normally we say that future directed is here. So if I'm going to take a basis, I'm going to always just try to choose this basis so that the 0 component positive means future directed. And this would be past directed. So the length, the absolute value of x naught is larger than the space length, but it's pointing up now. So causal vectors would be the vectors inside plus the boundary, right? So these are the null vectors. Again, there are null past directed and null future directed. And space like is everything else, and 0 is there. Okay. Good. So this is the causal character of vectors. And in each tangent space, it's very clean, right? So you have a nice smooth surface, smooth except at this point, which separates time-like or causal vectors from space-like ones. So now let's go back to the definition of a space-time. A Lorentzian manifold is called a space-time. A space-time if we can make a continuous choice of future directed vectors on this manifold. A space-time if a continuous choice of future can be made. This choice of future vectors can be made. Well, future, of course, means already causal, right? So space-like vectors, space-like, they cannot be future or past, or future cones can be made. Actually, you see one more reason just not to include 0 in the definition of causal, then it will be connected, right? Good. So what is the issue? Let me just try to remove my belt and hope for the best. So this is an example of a Lorentzian manifold, which is a space-time. So this is a flat manifold, and time goes up, and space goes sideways, and the metric is just minus dt squared plus dx squared. And if I identify it like that, then this is a nice manifold where I say pointing upwards is future. Right? But now you take the Möbius band, so you just do your usual identification after twisting. And if this is my forwards pointing direction, then when I come back to myself, it's going to be time up, right? So this is the Möbius band with this metric where the time flows transversally to my belt is an example of a Lorentzian manifold, which is not a space-time. Of course, but the Möbius one is and I do the Möbius identification, it's not a space-time. And note that the same Möbius metric, if I multiply my metric by -1, so that now time flows here, then it is a space-time, right? So if I just, even though the time, this Möbius identification prevents you to have a space orientability, but it has a well-defined time direction. Good, I hope that I'm happy my trousers didn't fall off. So good. So there is an obstruction sometimes, and one can ask the question, when is there an obstruction, if at all? Well, there's an obvious way to construct Lorentzian metrics using Riemannian ones. And so I'm talking regardless of field equations, right? So the question is, you have a manifold, can you have a Lorentzian metric? So you've just seen an example where you can't, if you insist on the direction being something. But in general, I think I have a Möbius problem with my belt now, but worry about it later. Right, so now maybe a useful fact, which we're going to use throughout the lectures, is that every manifold carries a Riemannian metric. Manifold carries a complete Riemannian metric. And that's fairly easy to prove, because if, well, on every coordinate patch you have a Riemannian metric. If you take, if you make a convex combination of Riemannian metrics, they remain Riemannian. So you just patch them together by the partition of unity. So you get a Riemannian metric. And to make it complete, you just use some conformal factor which blows up. If it's not complete already, you just multiply it by a conformal factor which will blow up as you go to infinity to make sure that, the metric is complete. So this is fairly easy now. And now how can you construct a Lorentzian metric? So by the way, I'll be using this complete Riemannian metric in a lot of places. So take a manifold, choose one, okay? You know that there exists one. It will not be important for what I'm doing, but I'm going to use it all the time. So let's choose one. Then how can I construct a Lorentzian metric out of it? Well, suppose that there exists an over-vanishing Killing vector. Suppose that there exists an over-vanishing vector, x, which is nowhere vanishing. And so call this metric H. Then you write G is going to be H plus X tensor product with X divided actually minus and minus 2. The length of H length of X like that, okay? So this is clearly a Lorentzian metric, because if you take an orthonormal frame of G, so EA is ON with X being the first vector, but then if I calculate G of XX, well, G being proportional to the first vector, you can always make a orthogonalization. What do you call this? Orthogonalization. What's the name? Schmidt, thanks. Graham. Yes. Right. Yeah. Okay. So good. Yeah. Thanks. Okay. So this should be X. B is H of X dot. Thanks. So in coordinates, if you are used, then that would be Gij is Hij minus 2xi xj over the length of X, the metric H squared. Okay. So if I calculate G of E0, then this is, well, actually x is proportional to E0 and x0 is not zero. So E0 is x divided by x0. So I'm going to get h of x divided by x0 square. And this will be minus 2 h of, well, E0, well, of x with the argument which is x twice. So normally should be, yeah, minus 1, I think. Minus 1. And then if you're orthogonal to x, then this is just h, right? So the dimension directions orthogonal to h will be Riemannian. So this is a Lorentzian metric. So you see that if there exists a nowhere vanishing vector field, then there exists a Lorentzian metric, right? So is there an abstraction to this? Well, if M is compact, non-compact, there always exists non-vanishing vector fields. I don't remember whose theorem is this, but there is a theorem like that. Such vector fields without zeros. So on non-compact manifolds, you always get Lorentzian metrics without zeros. And right, and if M is not compact, then there is an abstraction that's the Euler characteristic, right? So M compact, then you need I of M equals 0 for this. And let me say that this theorem, this part is completely uninteresting for physics. For once, I will just mention the theorem which says that causality is badly violated on every compact manifold. So if you want to do reasonable physics, you want causality. So this is not interesting, but I mean, mathematically, that's the statement. Now, but this is so far for the Lorentzian metrics. What about space-time? Well, so if you have a vector like that, you have an obvious choice. You're going to say, well, at every point I have a vector which is time-like in my metric, right? And then the one which is sitting in this component at the future. Right? So vectors aligned along x are in the future. So if you have a non-zero vanishing vector field, they always have space-time, right? So exists x, so exists a space-time structure. And actually it works both ways. Because if you have a space-time structure, so in other words, at every point you have a preferred cone of time-like vectors, then at every point you have a vector, non-zero vector, which points here. And because these cones are convex, again, by taking convex linear combinations, you can globalize this from one point to another and find a non-zero vector, right? So once again, so if you at every point you have a preferred cone like that, then you choose a vector here. And if you have another coordinate patch in which you have such vectors, then on the overlap, a convex linear combination of the vector coming from this cone and the one coming from that cone will be time-like again, because this is a convex, so you make a partition of unity and you get a space-time structure. Good, so we have space-times. We can start doing physics. And so for this, this was, by the way, section 1.1, and which is about space-times. And we can go to curves. So, what is a curve? A curve, or for me, the curve and the path is the same. Or path. Some authors make the distinction, but I'm not going to make it here. So this is a map. This is a continuous map from an interval to your manifold. An interval being what it is. And so you're given a manifold. These are curves or paths. And now we'll be interested in something which are causal paths. So, so there's an obvious idea. Well, let's see, a time-like path would be, well, a differentiable path so that its tangent is time-like everywhere. And then time-like consistently oriented. You don't want a path which goes zigzags in time. So, so let's try this definition here. Time-like curve, time-like future directed. So there could be future or past directed. Is a differentiable curve, but actually I'm not going to take curves to be differentiable, but piecewise differentiable. So that its tangent is time-like everywhere, right? With, let's say, gamma with gamma dots time-like everywhere. And the reason you want to allow piecewise differentiable is that, think about me walking here in this room. So physics, well, time-like curves are supposed to be curves on which physical objects live, right? So I'm a physical object, so I cannot go faster than the speed of light. This cone here is actually what determines the speed of light. So going slow means not doing anything in this coordinate system, right? So I cannot go faster than the speed of light. So the tangent to my to the curve I'm describing in space-time should be time-like. But of course, I can just stop here for a moment and start walking, and then my curve will certainly not be differentiable. But a good approximation may be piecewise differentiable, right? So you want to allow things like that to describe physical objects. Then, and of course, so I'm thinking when I'm saying just time-like curve, then it is either future directed, past directed, but it's not allowed, right, to zigzag in time. Okay, so that's that would be time-like curves, and that's good enough. Now, if you want to do causality theory, so unravel the causal structure of space-time, you have to take limits of curves. And if you take a limit of piecewise differentiable curves, it's unlikely that you're going to get something which is piecewise differentiable. So it's good to get a family of curves to work with, which is more general than this. And these are local Lipschitz curves. So let's see, so a curve will be called Lipschitz. Gamma, which is from an interval to M, is called Lipschitz. If there exists a constant C, so that gamma of S, well, I take 2 points on this curve. Gamma of S is here, gamma of T is here. Then I take the distance between these points with my favorite chosen Riemannian metric, and this should be smaller than T times S minus T. So that's a Lipschitz curve. If this curve happens to be differentiable, then this is obviously true by the mean value theorem or something like that, or Rolle theorem, some elementary theorems of differentiable functions. If it's piecewise differentiable, then this constant here may vary from piece to piece, but will still be true. So certainly, piecewise differentiable curves are Lipschitz. Now, Actually, I would need also locally Lipschitz. So is locally Lipschitz. Yes? Oh, sorry, distance, the h distance. Yeah, thanks. Yeah, thanks. Thanks a lot. Right, so you have 2 points here. You take the distance between these points, but thanks a lot, between the anything Riemannian. At this stage, for this definition, I don't even need complete, but it's useful to have complete for applications when I'm proving things and something like that. I'm not going to be proving things here, but I'm going to be stating facts which would not be true if the metric is not complete. Good. So this is locally Lipschitz. If for every compact subinterval of I, right? So okay, compact. There exists C of K such that star holds. So in other words, maybe globally this isn't true, but at every compact. What is the property of the curve? Right, yeah. The curve is Lipschitz if the length between any its 2 points is. That's the definition. Yeah, okay, sure, yes, okay. No, but my condition is this. The distance function restricted to the curve is Lipschitz. Okay, that would be one way of saying this. Maybe. No, but I like to understand you because maybe I'm missing something. So, okay, let me just say the following. If the curve is differentiable, this will be true, right? We agree with this. So you're saying a curve like this. Good. Okay. So if I take this curve, I start from here, I come back. This is obviously not going to be Lipschitz in my sense of my definition. Yes, I agree with you. Right? Because of course the distance is between these points is 0. Oh, it is Lipschitz. Oh, good. Okay. I'm relieved. This is my curve. And I agree that the distance between these points is, of course, not the distance along the curve. Right, yeah. But that's still my definition. Yeah, okay. Good. So good. And so locally Lipschitz, if this is true for ST in a compact, right? So for holds for is. Okay. Right. So not for my purposes. So in other words, on every compact set of your manifold, if you change your metrics, this will be risky. The distance will be, this will define equivalent distances, right? Right, so on compact set, it doesn't matter. It matters on non-compact sets, and you're right, but actually maybe the fact which is most relevant here is the following, and then it probably just also clears up this problem that if you have a Lipschitz or locally Lipschitz curve can be reparametrized by distance along this curve. Lipschitz curve be reparametrized. And this is not completely obvious, not distance in space, but distance along the curve, right? So in other words, this C can be chosen to be 1. So this distance will be, you're saying this will be longer, right? Yes. Okay, good. Okay. Okay, okay. So yeah, good. So in the sense that the length, okay, so let me just say for this, by distance along the curve. And for this, the key here is something that is useful all over the place, is the Rademacher theorem. Is that every, well, it's more general, but in my context, that every Lipschitz curve, locally Lipschitz curve, is differentiable almost everywhere. Almost everywhere. Right, and the so at almost every point you have a derivative, and this almost everywhere defined derivative integrates the functions. So and if you think of local coordinates, gamma I of S gamma A of t is the integral from S to t on compact intervals of this derivative, right? So there is a distributional derivative if you want to, or almost everywhere pointwise derivative. Obviously, it's L infinity because of this inequality here. Right, so it's this gamma dot in L infinity, gamma dot in L infinity log. So gamma dot defined almost everywhere and bounded almost everywhere on every compact subset. This is in local coordinates in every coordinate pattern. So you can write this like that. So right, a complete Lorentzian metric, I doubt it. I don't know. Every closed manifold. Oh, you mean compact manifold? No, it's wrong. Yeah, it's wrong. Yeah, it's wrong. No, but even there are examples of compact manifolds, smooth compact Lorentzian manifolds, which are geodesically incomplete. What happens is that so what do you think is the Hopf-Rinow theorem, right? Every complete metric on every Riemannian metric on a compact manifold is complete. Right? That's Hopf-Rinow. and that's wrong for Lorentzian. Yeah, there are examples where that's not true. So compact, smooth, Lorentzian, and not geodesically complete. I don't know. Right, because the example is a geodesic which accumulates on a null curve, and you're changing by a compact factor. The null geodesic null curve remains a geodesic. Well, okay. I mean, certainly it's probably true that you cannot have fixed it by a conformal factor. Good. Yes. Okay. So in other words, these locally Lipschitz curves are as good as you. As if they were differentiable, right? If you want to do something with them, so you want to maybe differentiate them and integrate, well, this formula is true, even though this thing is not defined everywhere. So that's this. And now when you have that, you can change your parameter, not that this constant is 1, but the length of the reparameterize the curve so that the length of the tangent is 1 almost everywhere. So this lambda, choose a parametrization so that gamma dot is 1. So in this sense, that's the distance in this sense, so that you're absolutely right that it could be, this is longer than going from here to there, but you have good control over compact sets. So. I'm sorry, I have to do something with this Mobius belt because my trousers are going to fall off. No, this is always this H, right? So this is H. I'm probably not going to write Lorentzian norms in this lecture. We've chosen 1 and 4 a metric, and which does this. Good. Good. So now we have our curves. So I'm going to take causal curves to be Lipschitz curves, so that this the tangent is null wherever, almost everywhere, where defined, right? So it's not defined everywhere; it's defined almost everywhere, and maybe it's not. Then once when it's defined almost everywhere, it's not causal everywhere in this set, but so up to another set of 0 measure. This should be a causal vector, and of course consistently oriented, right? So now just keep this. So right, so gamma is causal if locally Lipschitz and gamma dot is well, future or past, I'm going to add here, but gamma is causal almost everywhere. I mean, the key fact here is that causal curves are closed in a certain sense, which is essentially Artella-Ascoli. And in the certain sense, one has to be careful about parametrizations and stuff like that. So from now on, I'm going to assume that this is the parametrization I'm using, right? So you have a sequence gamma n, well-parametrized causal curves. And well-parametrized means that the length of the tangent is 1 wherever defined. Parameterized causal curves. Say future, just to make sure, future directed causal curves. So, and we have that we have a point P, so that we have gamma 1 here, gamma 2, gamma n. This is gamma n of 0. And there exists a point so that they all converge to some point. Then there exists a limit curve, a causal curve through P. Right, which so that and a subsequence and let's see, they're well parameterized future and let me just take them in extendable for fun, and let me just so that I don't want to have problems. So the gamma n's in extendable means that they're defined from R to M. Right? So this parameter range on which they're defined, it's not only an interval, but they're in extendable. So you cannot go further than this. They're defined from R to M. Pass causal curve through P, and for every such that for every compact, say, well, compact in R, the distance of gamma n, the causal curve gamma of S, gamma of S, take the soup, so the goes to 0. So subsequence, okay. For every car, there exists a subsequence, gamma and I. But that is limit as I goes to infinity, goes to 0. Okay, so in other words, whenever you have a sequence of curves like that, you can find a subsequence which converge in the compact open topology. Okay, that's the fancy word here. But in other words, if you take, they're all defined for all parameters in R, but you just take from, say, minus 2000 to 2000, you can find a subsequence it converges in a C0 to this curve. And then, I mean, the proof is essentially Arcella-Ascoli, but you still need to, well, you have to use the fact that they're causal and inextendable and things like that, which I'm not going to, and well parameterized, which I'm not going to go into in details. But this is the main tool of causality theory, right? So if you want to do causality theory, that the main thing which you use to prove properties of let's see. So, so do you have something similar for any? Because if it's space-like, essentially you can just take any family of Lipschitz curves, right? Some locally Lipschitz curves converging in one point. There exists something which converges. Imagine various pathologies with spirals and things like that. So one thing which happens when you're dealing with causal curves, you have to remember that locally they always have to go up, right? So they cannot spiral back on yourself, and that's part of the things which happen here. So I could imagine that if you allow spiraling, you can have terrible things. Which are, but offhand, I don't know. I haven't thought about this. Certainly not for a while. So this is the main tool to play with when you're talking about causality. And so now we can just define, okay. Is there another one? you can define chronological futures, chronological past, and start thinking about their properties. By the way, if you want to read about these things, a good reference would be a Ettore Minguzzi Living Review. Which has all, you can find there more that you want to know about, for instance, metrics, or where my lectures, what I'm talking about is mainly based on chapter 1 of my book, Geometry of Black Holes, which will be much less complete than Minguzzi, and therefore maybe, and much more pedagogical, therefore maybe more readable, but certainly that would be encyclopedical source of knowledge on these things, of black holes. Good, so let's see. So now what is the I plus of P? This is another definition. This is the chronological future of P. So P being a point in M. And this is the set of points. So you take a point P and you look at the set of points which can be reached by time-like curves starting from P. Q such that there exists a time-like future-directed time-like curve from P to Q. So that's this kind of set. Well, you can define the chronological past. I don't want to use this color because you can't see it well. So this would be past. And then time-like past-directed. Time-like future-directed. Probably too much emphasis on time-like here. Past-directed. And you can define the causal future. So J plus of P will be the causal. And then future and past is like before. And everything which will change is that this time-like goes to causal. So this is the basic sets you work with. Once we know the curves, so here the curves are rather simple. These are time-like piecewise differentiable. Here they're a little more complicated. They're Lipschitz, locally Lipschitz, but they're not that much more complicated because they're as good as differentiable everywhere. As far as integration is concerned, it doesn't see the sets of zero measure. Good. So 4 hours, right? I thought I had an hour. I don't have an hour. Oh, I see. I finished already. So let me just finish by a few definitions. And or maybe I just stop here and continue with a few definitions.